See, in the first video, I had dealt with a magnetic moment of a revolving electron, where magnetic moment, very, very important, magnetic moment itself is Ia. It's Nia, but N is 1. So Ia, I is equal to Q by T, area is pi r square, T is equal to 2 pi r by B. So pi and pi get cancelled, r and r get cancelled, QVr by 2 is the magnetic moment. You already know Vr is equal to L by M. Q by 2 into L by M is known as magnetic moment, and since it's a vector you have to put it like this, because when an electron is going around the nucleus, if it's going like this, by right hand thumb rule the curled finger is like this, then the thumb will be upward, and that will give you the direction of the magnetic moment. Magnetic moment is a vector because area in physics is a vector, and so area's direction will be like this. If the electron is going like this, then the magnetic moment will be downward, and angular momentum is always going to be on opposite direction. That's what this negative sign means. And you know, here L can be written as minus Q by 2m into NH by 2 pi. N is equal to 1. If you put, you get minus QH by 4 pi m, NH by 2 pi. Okay, so 4 pi m, and this value is known as Bohr's magneton. Bohr's magneton. I remember magnetron, I taught you till here. And today what I'm going to do is, there's also another derivation which is there in the previous video, but it's not there in portion, to show that a solenoid behaves like a bar magnet. That's been omitted, but you know, a solenoid actually behaves like a bar magnet. So that's what it is, and you don't need that derivation. So today what I'm going to teach you is the second part, where, you know, deep under the earth you have to imagine that there is a magnet whose south pole is here, north pole is here. Why? Because when you freely suspend a magnet, it comes to rest in north-south direction. Why does it not come here? Because the earth, underneath the earth, the south is here, so it's attracting. So this is called geographic axis. Geographic axis. And this is called magnetic axis. You can ask me, will there be really a bar magnet which is under the earth? No. The earth consists of ferromagnetic substances. So ferric oxide, Fe2O3, Fe2O4 in molten form. Okay, and the molten form is there, and on the surface of the earth there are charges. As the earth spins, the charges are also flowing, which constitute current, and therefore it behaves like an electromagnet. And so you can imagine the earth to be buried underneath a bar magnet. So then this is known as geographic axis and magnetic axis. So what is, let's draw the magnetic axis straight here, and let's draw the geographic axis, what is straight here, let's draw it slanting here. This is geographic meridian. Vertical plane is called meridian, and this is called magnetic meridian, a vertical plane passing through the axis. You know that, I taught you. And this angle between them is called theta, which is angle of declination. Angle of declination. And this is like a notebook. If you can see, there will be a resultant which is going through like that, which is B between the notebook papers. And therefore this B will be of two components. One is B horizontal, another is B vertical. And the angle delta that the B makes with the horizontal is known as dip angle. Dip. So these are the things which you should know. The angle of declination, dip, the magnetic meridian, the geographic meridian, all these terms, and what are those you should know. From this you can see that a cos delta is equal to BH by B. So BH is equal to B cos delta. A sin delta is equal to BV by B. So BV is equal to B sin delta. And you also, the resultant is equal to BV square plus BH square. Okay, next is so idella components. What are the various components? You know, angle of declination, angle of dip, then what else? You know that geographic meridian, magnetic meridian. These are all the various components of the Earth's magnetic field. And coming back here, let me the deep under the earth, there is this pole. This is south and this is north. And you know, with bar magnet, outside the bar magnet, the field length goes from north to south. It's like this. Within the bar magnet goes from south to north. Okay, now if you see, the earth is going to be like this. So if here you see this and the earth's surface have an angle. This is the dip angle. This is the dip needle. and the dip needle makes an angle with the horizontal component, and that's called delta. So at the equator, delta will be 0 because this dip needle and the surface of the earth will be parallel to each other. So there is no vertical component, only the horizontal component exists. At the poles, you see the theta will be 90 because dip needle is perpendicular to the surface of the earth. So theta is 90. So only the vertical component will exist, horizontal component will not even exist. At the this is at the equator and this is at the poles. So you should understand all this. Next is I'll teach you the various terms involved is B, H and I. What is B is magnetic induction. Magnetic induction or magnetic field strength. Field strength. The SI unit will be Tesla. It's also Weber per meter square, which shows that flux passing through unit area is known as magnetic induction. Okay, next you should know this formula. Mu is equal to B by H. Very, very important from the first equation. From the second one is known as magnetic intensity. Magnetic intensity. Magnetic intensity is to do with the field, is related to the field, an extent to which a field can magnetize a substance. A field can magnetize a substance. It's field related. It's mainly field related. SI unit is ampere per meter. So let's talk about this. This is the intensity of magnetization. Intensity of magnetization is actually specimen related. Whether you're keeping an iron or a copper, depending on what extent it can get magnetized. Specimen. So extent to which the specimen can get magnetized. The capacity to see, so your observing ability will be different. Patricia's will be different. So it is all specimen related. The field is the same, which is Malthian-T. Correct? It's like that. The extent to which specimen can get magnetized. Specimen can get magnetized. Are you clear? And that SI unit is also ampere per meter only. And next is susceptibility, is I by H. It's the ratio of intensity of magnetization to magnetic intensity, I by H. Therefore, it is no dimension because ampere per meter will get cancelled. This is known as susceptibility. Next, if you keep you take a field and so you take a field and keep a specimen. This specimen can get magnetized because of its ability to magnetize itself, and also the extent to which the field can get itself magnetized. So then the B is coming because of Bi as well as because of BH. And you already know mu is equal to B by H. So B is mu into H. But in this case, it's mu into I. Mu naught into I. Actually, let's say mu naught. Let's not say mu. It's mu naught is equal to B by H. So B is equal to mu naught into H. But in this case, it's mu naught into I. And in this case, it's mu naught into H. From this, what you do, you take mu naught and H out. So that you get I by H plus 1. Okay, and so I by H. So I by H itself is susceptibility. Correct? Now you should write mu into H, left side. So that H and H gets cancelled. Mu by mu naught is equal to susceptibility plus 1, which is mu r is equal to susceptibility plus 1. It's a very, very important question. They'll give you some value for susceptibility. They'll ask you to find the value of relative permeability, magnetic field. Sometimes they'll give you this, they'll ask you for susceptibility, in which case you have to subtract it. Okay. Correct? So then that's about it. Next is this derivation is very important. Then is difference between dia, para and ferro. Dia, para and ferromagnetic substance. Okay, diamagnetic substance, when you suspend a diamagnetic specimen in a magnetic field, it will come to rest in a direction perpendicular to the magnetic field. Whereas a paramagnetic substance, when you suspend, will come to rest in the same direction as the magnetic field. Same, ferro and para are more or less the same way. Okay, next is this is first point. Second point, when you place a paramagnetic substance, a diamagnetic substance in a magnetic field, the magnetic field line will get expelled like this. Whereas when you place this is about a ferromagnetic substance, the field lines will contract. Para means so many lines will go through, not just one, so many lines, very strongly magnetized. Next point, when you place a diamagnetic substance in a magnetic field which is like this, not only the field lines is getting expelled, the diamagnetic substance get magnetized in the opposite direction, that too weakly magnetized. I forgot to say this point when I was teaching, weakly magnetized in opposite direction. It gets weakly magnetized in opposite direction, whereas a paramagnetic substance get magnetized in the same, weakly magnetized in the same direction, whereas this is strongly magnetized in the same direction. Strongly magnetized in the same direction. This is the third point. Let's go to fourth point. Fourth point is, as I told you, it moves from Diana moves from stronger to weaker. So then therefore you take a magnet, both magnet here, North Pole and South Pole, say in this North Pole and South Pole, take a china clay in which have a molten diamagnetic substance. You know that moves from stronger to weaker. Here is stronger field between the poles and here it is weaker. So then moves from stronger to weaker, it will move here and it will be small, it will be concave here and it will be smaller here, it will be larger quantity in weaker portion. When you move this magnet away, there will be weak magnetic field at the center and strong magnetic field at the ends, and therefore it will be bulged here and it will be lesser here. That's how a diamagnetic substance behaves. Like para is opposite of this. So you just have to draw this and draw the opposite of it in para. South and north is here, and you know it's stronger here and weaker here. This moves from weaker to stronger, so it should be convex here and a small surface here. And when moved away, the contra of it. Are you clear? So then, and the example of a diamagnetic is anything Diana, so glittery, such as zinc, gold, and copper. Paramagnetic is aluminium, magnesium, and all that. And for ferromagnetic is cobalt, nickel, iron, all strong metals. Okay, iron. Or all examples of. Okay. Next, the sixth question. Sixth difference is. I think we have to talk about susceptibility is slightly negative. Susceptibility is slightly positive for this. And it's much greater positive value. So which means the relative permeability is less than 1, slightly less than 1. Relative permeability is slightly greater than 1. When they give 1.001 and all, it will be paramagnetic. When they give you 3.4 or some 1000 or whatever value, that will be ferromagnetic, much greater than 1. Then the last is susceptibility versus Curie temperature. The graph is independent for dia, whereas it is dependent for para and ferro. These are the different example. And why does a magnet behave like a magnet? Why? Okay, first of all, I'll tell you another one point we should know. In paramagnetic, it's the presence of unpaired electron will be there. Unpaired electron. You know 1s2, 2s2, 2p6, you would have studied in chemistry. The last orbital electron will remain unpaired. In such a case is what results in para, whereas dia is completely paired electron. Okay, so that's the main point. And what makes a magnet is, like, you know, every atom consists of free electrons. And these free electrons are orbiting in dumbbell shape according to chemistry. Yeah, the dumbbell 1s2, 2s2, 2p6 format. The dumbbell keeps orbiting subshells, you call it, no? Okay, whatever, it keeps orbiting, and because of which is a current. The electrons are moving, constitute a current. Okay, so which means there is a magnetic moment. Correct? So the thing is, when these electrons, the orbiting or aligning in random order, it will not form a magnet. For some metals, for some substances, it will align itself orient itself in a particular direction. The orientation of these electrons will be in one direction. Therefore, it will be one end will behave like a north pole, other end will behave like a south pole. It's the orientation of these electrons which attributes and makes it a magnet or a non-magnetic substance. What attributes to it? You understood? So the last but not the least is only one numerical in this lesson. They'll ask you in different ways, but the question will be the same. The question will be different, but the answer will be the same. Sorry. They'll talk about a compass needle or a needle placed at a point O. The moment they give you a needle like this, you know this is north pole and this is south pole. They will give you a magnetic moment at a point P. Supposing they are giving it in this direction, calling it M1. They'll ask you what is torque. Torque formula is mb sin theta, for which you should know the magnetic field's direction. The magnetic field at this point is the equatorial line. This is like a dipole itself. Yeah, the north pole here and south pole here. At the equatorial line, the field will be in this direction away from the south pole. So you can see that the magnetic field will be like this. The theta is equal to 0. When theta is 0, torque will be 0. But the potential energy is minus mb cos theta. And cos 0 is 1, so it will be minimum potential energy. Minimum potential energy stands for stable equilibrium. Maximum potential energy stands for unstable equilibrium. Like that, they will give different points. Say they might give you a magnetic, they will give you a magnetic moment m2 like this at this point q. You know the magnetic field at this point is like this. Correct? It's what is the formula? Mu naught by 4 pi into m by r cube at the equatorial line. B's formula. But you know that they both are making an angle 90 degrees. So torque will be there, mb. But the potential energy will become 0. Like this, they will give you at this point. At this point, there's a numerical in the textbook. You have to make sure that you're finding the torque and the potential energy at those respective points. So one and only questions will come for board exam.